Hello guys, hello. It is time to jump into properties of logarithms. Okay, these are the properties that are going to allow us to understand logs a little bit better so that when we get to solving them, we'll have some neat little shortcuts to help us work it out. Okay, all right, so 5.4 is going to be talking about the product rule, the quotient rule, and the power rule. Okay, so we're going to talk about those, and then we're going to look at expanding and condensing. I think that may be pretty much all of 5.4. We're going to touch on change of base as well. Okay, all right, so let's just dive right in because that's what we like to do. So properties of logarithms, I went ahead and just wrote them out for you. Okay, the product rule says that if there is a multiplication inside the log, okay, not outside, inside the log, meaning you have log base A or log of something being multiplied. So I'm just gonna write that as a multiplication dot. Okay, what you can do is you can actually separate that into two separate terms. So we do log base A of the first factor in here plus log base A of the second factor. So what this tells me is that when I have a multiplication inside a log, this turns into an addition of log terms. Okay, now we're going to use this rule going both directions. So we may have a multiplication and they may ask us to expand it. So if they ask us to expand it, then we would write it as two separate log terms. Or there might be times when we need to condense it, meaning we have two log terms, but we'd rather just have one. So if we can see that these are the same log bases and they're being added together, then we can write those inside values as a multiplication to condense it down to one log. Okay? All right, same thing with the quotient rule. Notice the only difference from the last rule to this rule is that now instead of a multiplication, we have a division, right? So if we have a division inside the log, what happens is that that can turn into a subtraction of log terms. Okay. Now it is important to make sure you know which one is subtracting which one, because that makes a big difference. So notice the factor that's on top. So here the m is the positive term, and the factor that was on bottom is the log term that's now being subtracted. Okay, so just like the last term, we're going to use this one both ways, right? If we have a division, we need to be able to expand it into a subtraction of two terms, or if we have a subtraction of two terms, we need to be able to put it back into a division or a quotient inside a log, right? And then the last one we have is the power rule. And this says that if we have a log and on our inside factor here, we have multiple copies, or in other words, we have an exponent on that factor, we can actually pull that power down as a coefficient. Okay, and let me explain to you why. Let me just explain to you why. Okay, so when you have an inside factor that is raised to several powers, right, or to a power, means you have multiple copies. So let's pretend, just for example's sake, let's say you have log of 3 to the 4th power. Okay, well, what this really means is that you have log of 3 times 3 times 3 times 3, right? You have 4 copies of that 3. So that is a multiplication, right? And we know that when we have a multiplication or a product, multiplication turns into addition of terms. So I could actually write this as log 3 plus log 3 plus log 3 plus log 3. Right? Using my product rule. Because anytime I have something multiplied in here, I can write its own individual log term for each factor and just add them. Okay? So notice if I add them up, how many am I going to end up with, right? I have 1 log 3. This is going to give me 2 log 3. This is going to give me 3 log 3. And this is going to give me 4, right? 1, 2, 3, 4. So I end up with 4 log 3. So this is basically, I'm just showing you how this works, right? Why this works is whatever this exponent is tells you how many copies of that factor you have is going to tell you basically how many of those log terms you're going to end up with. So this is really good if we're trying to shrink this all down into one condensed log term. We can take this 4 and put it back up in the exponent. Or if we're trying to expand it out, right, we can take any exponent on a factor and bring it down. Okay. Now it is important to note that we can only bring this down if that exponent is on this entire inside value. Okay. So if there's several bases that have several different exponents, we need to use the product rule or the quotient rule to separate them into their own individual terms, and then we can get rid of the exponents. Okay. All right. So let's look at putting these into use. So now this one, and I will say this on a lot of these log problems, there are multiple ways of solving them. When you take your exams, I am grading that you show me right, your method for solving. So those of you who have either snuck in a calculator or went and got some sneaky little calculator that will do logs for you, if you just give me an answer, you will just get no credit. Okay, so you have to show me something you know, demonstrate some kind of steps onto how you solved it. Okay, but just because you use a different solving method than your friend doesn't mean that you did it incorrectly, because there's lots of ways to solve these. So let's look at this first one. The first thing that I notice personally is that I have log 10, right? That stands out to me because I know that when we have a log and the little subscript value, there's nothing written there, that's a log base 10, right? So this is the same thing as saying 1/6 times log base 10 of 10 to the 6th, right? And we know that when we have log base 10 of 10, those cancel out, right? Because those are inverse functions that are canceling one another out. So that leaves me with 1/6 times 6, and 1/6 of 6, right, is 1. Or you can multiply it and get 6 over 6 and then reduce it down to 1. Okay, so that's one way of working it. Another way, for those of you who may have not done it this way, is if we have 1/6 log 10 to the 6th, right? This last power rule that we just learned says that if I have an exponent on the inside factor of my log, I can bring that exponent power down as a coefficient, meaning I can bring this 6 down in front of this log. So that means that I would have 6 times 1/6 log 10, right? And then 1/6 and 6th, I could go ahead and make, multiply that, which gives me 1 log 10, right? And then log 10, remember, that just cancels out. So you can either cancel it out, or you can say it cancels out to be 1, technically, right? And then 1 times 1, again, is just 1. So whichever method stands out to you more, use what's easiest in your brain, okay? Let's look at another one. Now this one may not stand out as anything we can do easily in our brain because, again, we don't have a subscript, so that means this is a common log. It's log base 10, but notice 40 is not a power of 10, and same thing over here, 5/2 is not a power of 10. So that really kind of doesn't help me. So what I'm going to look at is the fact that I see an addition of log terms. Okay, so I'm going to look back up here at my rules, and the only time I see an addition here is on my my product rule. My product rule says that if I have an addition here, I can convert that to 1 log with a multiplication, right? Or if I have a multiplication, I can turn it into an addition. So what I have is an addition. So my problem is actually starting from this side, and I can simplify it by moving it back into a single log. So an addition means that I would have had to have multiplied those inside factors. So if I want to write this inside 1 log, then I need to multiply the factors from each log term. Okay. Now notice, once I do that as a multiplication, I'm only writing log out front 1 time, right? I'm not writing log of 40 times log of 5 over 2. No. Because our product rule, notice it only has log written once, and then we're multiplying our inside values. Okay. So from here, now we should be able to simplify this, right? Because these are just regular numbers. So we can multiply straight across if we want and do 40 times 5 and then divide that by 2. Or I'm going to go ahead and just reduce, because I know that 2 goes into 40 20 times. right? If I reduce this 2 and that 4, 2 goes into 40 20 times, and then I still have the 5 left on top. So this gives me log of 100 when I simplify, okay? And then just like all my other problems, I want to make sure that my log is completely simplified before I circle my answer. And notice here, a log with no little subscript is a common log base 10. And 100 is a power of 10. So I'm going to go ahead and just rewrite this as log, and I'm just going to put the little base 10 in there just so it kind of reminds those of you who have slept since the last video that I can write this 100 as 10 squared, right? It's a power of 10. So 10 squared. And then anytime I have log base 10 of 10, those are inverse functions, so I can cancel those. So this just equals 2. Okay. All right, I want to show you about 3 more exercising these same properties, and then I'll have y'all try some, okay? All right, so on the top of page 28, we're looking, and notice, and I have an ln. ln, remember, is our natural log. So if you see ln x, right, that's the same thing as log base e of x. ln means log base e. So the only time that I can cancel out an ln is if I have an e on the inside of that. So if I look at these, this does not have an e inside, right? And I can't write that as e to some power. This one does not have an e inside, so I can't write that as some power of e. So there's really no chance of canceling out these ln's. So I want to go to the next best thing, which is let's just try to condense this down to one term and see what that does for us, okay? So if I take these two terms, notice right here, I have a subtraction, right? And subtraction, if I look back at my properties, when I see a subtraction, the subtraction symbol comes from originally having a division of factors within my log, right? So whatever my first term, my positive term is, that factor goes on the top of my quotient, and the term that's getting subtracted, its inside factor, goes into the denominator of my term, right, of my inside value here. So I'm going to go ahead and apply that to this one. So if I want to write this as one single ln term, I know that it was a quotient because I see the subtraction, and the positive term, my x cubed, goes on top, and the term that's being subtracted is the one that goes on bottom, 2x. Okay. And then I just look to see if there's anything I can do to simplify. Obviously, we already talked about this is not an e, so I'm not going to be able to cancel out the ln. But notice I do have common factors on top and bottom. I can reduce 1x on top and bottom, right? Or in other words, for those of you, again, who have slept, x cubed is the same thing as x times x squared, right? And on bottom 2x is the same thing as x times 2. So I can reduce by x on top and bottom, which means that my final answer for this one is just going to be ln of x squared over 2. And although it may not look that pretty, it actually is a little bit more simplified than the mess we started out with. Okay, so this is my solution. Let's look at a couple more where it's having us condense these log terms down into one term to simplify it. So on this one, again, I see that I have a subtraction. A subtraction lets me know that I must have started with a quotient, right? Just like on this one, when I subtracted, I turned it into a quotient. So I know I can do that. But if you look at my quotient rule, just to flip back, my quotient rule only works if I have a log with no coefficient, right? And then I have log terms with no coefficients, right? I have a subtraction of log terms that turns into a quotient, but there's no numbers in front of these log terms. So if you look at the one I'm trying to work, I have a 2 in front of this log and a 3 in front of that log. So I can't use my quotient rule until I get rid of those coefficients. And the only way to get rid of a coefficient is to use my power rule. So remember, the power rule says that if I have an exponent, I can bring it down in front, it also says that if I have something in front, I can put it back up in the exponent. So that's what I'm going to do for this second example. I'm going to take this 2 and put it back up in the exponent of my x. And I'm going to take this 3 and put it back up in the exponent of my y. So that's going to look like log base 4 of x squared, right? Because I'm just putting this 2 up in the exponent, minus, now I'm not going to take the minus with me because the minus tells me what rule to use next. So I'm just going to take the positive 3 up and leave the minus between the two terms. So minus log base 4 of y cubed. Okay. So now I have two terms that are being subtracted and they don't have coefficients. So now I can go ahead and mush it back into one log term and write it as a quotient. So this becomes log base 4 of, remember this subtraction tells me that it used to be a quotient. The one on top is my positive one, so x squared. And then the term that's being subtracted, its factor inside is what goes on the bottom, y cubed. Okay. And then I double check to make sure that this is as fully simplified as I can get it, right? Log base 4, I would need a 4 to some power to be able to cancel out this log. And you can see here I don't have any 4s or any powers of 4. And then x squared and y cubed does not simplify. So we just leave it like this. Okay. Let me look at one more and then I'll have you all try some. So looking at this next one, it looks a little bit different, right? Just a teensy weensy bit different because it has quantities inside the log. We haven't seen that yet. We've only seen single factors, right? But we still want to work this in the same way. Notice there's no log subscript on either of these. So if there's no log subscript written, that means it's a common log, or in other words, it's base 10. So in order for this log to cancel out, I would have to have 10 to some power on the inside. And we can clearly see we don't have 10 to some power on either of these. So moving on to our next strategy, which is this subtraction, right? Our subtraction tells us that this had to have been a quotient to begin with. And notice here, I don't have any numbers out front of the log. So I can go ahead and turn this back into a quotient. So when I squish it into one log, this subtraction tells me that I should have a fraction. The one that goes on top of my fraction is my positive term, which is my x squared minus 16. And the one that goes on the bottom is from the term that's getting subtracted. So its inside value here is x plus 4. Okay. So again, I can't cancel out my log because I don't have 10 to some power in here. But notice, we have simplified a rational expression that looks like this before, right? To simplify rational expressions, we factor top and bottom and reduce common factors. Okay, so when we have a rational expression where we have at least an x squared, we can always look to factor to see if we can reduce common factors. Now, in my denominator here, I just have an x plus 4. There's nothing I can do to factor that, make it more simple, right? But on top, this is a difference of squares, right? Difference of squares. And remember, a difference of squares, I just have to figure out what's my base that's being squared here, which is x, right? And what's my base that's being squared here, which is 4. And then I can plug it into that formula. So this gives me log of difference of squares formula. This will factor into x plus 4 times x minus 4. And then I still have that x plus 4 on bottom. Okay. So we can clearly see, right, that we have an x plus 4 on top and bottom. So we can reduce that factor, right? So this leaves us with log of x minus 4. And notice, because I have two separate terms in here, I still need to keep the parentheses around it. And I want to check and make sure it's as simplified as I possibly can get. And this one's a little bit tricky, right? Because we look at it, we might say, oh, look, we have a subtraction. And subtraction turns into quotient. But it doesn't, because here, notice, our subtraction is inside the log, right? If I look back at my properties, my subtraction here, the only rule I have that has subtraction is when the subtraction is being applied to log terms. Notice I don't have any rules for a subtraction inside the log. I only have a rule for multiplication in the log, or a quotient in the log, or an exponent in the log. I don't have a rule for subtraction inside the log, right? So that means for this last example, this is as simplified as it gets, okay? All right, so there are 3 on this next page for you to do. So go ahead and pause the video and give those a whirl when you're ready to check yourself, or if you get stuck, unpause it and I'll go over them, okay? Okay, let's see how you did. So on this first one, notice it's even telling you, use the properties to condense. When you see the word condense, that means you're taking several log terms and you're trying to squish it all down into one log term, okay? So when we condense this one, the first thing we have to do is get rid of the coefficients, because we can't use the product rule or the quotient rule to condense unless it's just regular logs with no coefficients. Excuse me. So I take this 3 and I put it back up into the exponent of the 2, which is what I did here. And I take this 2 and I put it back up into the exponent of the 4. Now that I've done that, because these are just regular numbers, I went ahead and multiplied it out. We know that 2 cubed is 8, 4 squared is 16. And then because we have a subtraction here, right, that means that we originally must have had a quotient. So we can go ahead and put our factor from within the first term on the top of the quotient, our factor from the second term being subtracted in the denominator of our quotient, and write it as one single log term. Okay. Now here my 7 is not, my log base 7 is not going to cancel out because this is not some power of 7, but we do want to go ahead and reduce this. 8/16 is 1/2. So we end up with log base 7 of 1/2. Okay. I'm going to go ahead and move on to the next one. As always, if you need to pause the video and look at it a little bit closer or work through it slower, feel free to do so, okay? All right, on the second one, same idea. I have to get rid of any coefficients that I have. So notice I don't have a coefficient here, not a problem. I do have a coefficient here, which is 2. And remember, when I stick it back up here, I'm putting it in the exponent. So notice here, like when I put the 3 up here, I was putting it in the exponent of the 2. This was 2 to the 3rd power, right? So I have to do the same thing here. When I put this 2 up in the exponent, notice it already has an exponent. So it's like I'm raising that exponent to an additional power. And when I raise a power to a power, I just multiply those exponents, right? So that's going to give me log base b of x to the -2, right? And now that I have 2 log terms with no coefficients that are being added, remember, addition tells me that I must have started with a product. So I can go ahead and write the inside factors of these 2 logs as a product within one condensed log. So I have log base b of 5 times x to the -2. And then I want to say like 9 times out of 10, if not 10 times out of 10, they won't let you enter your answer unless it has a positive exponent. So remember, the way that we take a negative exponent and turn it positive is we move it across the fraction line, okay, wherever the fraction line happens to be. Here there's not a denominator, so that means the fraction line is under the 5 x to the -2. So we're just going to move that x to the -2 down to the denominator, okay? All right, let's look at our third and final one. Hopefully you're doing good and hanging in there. This one is a natural log. You can see inside there's no power of e, so these natural logs are not going to cancel out. But I can go ahead and condense them because I have a subtraction. Subtraction condenses into a quotient. So I take the inside factor of my first term over the factor of my subtracted term. And again, I cannot stress this enough. When you condense it, you only write the log one time. Don't write log of this over log of this, okay? When you condense it, you're condensing it to one log, and you only take these inside factors in here, Okay, the log is only written once. And then from here, we want to go ahead and see if this will factor. Okay, if it will not factor, then you're done. You would just stop right here. But if you do your sum product chart, or whatever your factoring method is that you're super good at, right, you'll see that this one factors into x plus 5 times x minus 1, which means that we can reduce our x plus 5s on top and bottom, leaving us with ln of x minus 1. And even though we see that subtraction sign and we think, oh, we have a power or a product rule or a quotient rule, we have some kind of a rule that works for that, we don't. Because here our subtraction is inside the log and we only have a rule for subtraction outside the log. Okay, so we're done. All right, so those are the practice problems. Hopefully they weren't too bad. So if you notice on all of those problems, we were taking multiple logs and we were condensing it down into one, right? So what we're going to look at now is what happens when you have one log term and you want to like stretch it out or expand it into multiple log problems, log terms, okay? So here it says, use the properties of logs to expand the following expressions as much as possible, okay? So that means we don't want to be left with anything that we have a rule that we can fix, meaning if we have a multiplication, that needs to expand into addition. If we have a quotient, that needs to expand into subtraction. Or if we have an exponent, that needs to come down as a coefficient, okay? Our three rules we learned at the beginning of this section. So when I look at this, there is a lot going on, like a lot, right? So let's break it down into what we see first. The first thing that jumps out to me is that I have a fraction, right? Or in other words, I have a quotient, right? So if I have a quotient, I know that a quotient I can expand into two terms that are being subtracted, right? So I'm going to go ahead and turn this into a subtraction of log terms, okay? So I'm going to do log of the top factor, right? So that's what my quotient rule says, is that I can turn this into log of the top piece, which is the cube root of x, minus log of the bottom piece, which is x squared z. Okay? Okay, so now I have two terms. That looks a little bit better. But I still need to break up any multiplication and I still need to get rid of any powers, okay? So there's a couple of things that I can do here. First thing I see, I'm going to leave this mess alone, but I see that this has a multiplication. And we know that multiplication can be expanded, right, into addition, right? Which means I can create an addition term for this. So I'm going to go ahead and write this as log of the cube root of x minus. Now, this minus is important. Let me tell you why. Because it is subtracting this log. So if this log happens to turn into two terms, which is what we're doing, we're turning into an addition, we have to make sure that that negative is applied to both terms. So I'm going to put a parenthesis here, okay? So the first term I'm going to get here is going to be log of x squared plus log of z, right? Because we know a multiplication turns into addition. So the multiplication in here, I took those two terms and I gave them each their own log term, okay? All right. Now, the other thing I need to do, I do need to distribute this negative, but I also need to worry about this thing, okay? A cube root of x. There is a way to write that with fraction exponents. We went over this at the very beginning of the semester, and if you've slept since then, totally get it. So we're going to refresh, okay? When we have something like this, we can change this to a fraction exponent if we look at it in terms of its power over the root value, or over the index. Power over root. So if I look at this, I have an x that I have to the first power, right? I only have one x under that cube root. So 1x. That's my power. And my root is whatever my index value is on this on this radical, which is 3. So my power is 1, my root is 3. So instead of writing the cubed root of x, I could rewrite this as log of x to the 1/3 power. I could rewrite it with a fraction exponent. Okay, so going from here to here, I'm just using this fraction exponent rule that says I can write any radical, anything that's under a radical, right, in a fraction exponent form by just identifying what its power and its root is. So this is x to the 1/3, okay? And why that helps us is because now that's an exponent that using the power rule I can bring down out front, okay? All right, so let me go ahead and distribute this negative to both terms. So this becomes negative log of x squared minus log of z. Right? Which makes sense when we think about it, because notice the x squared and the z both came from the denominator originally, right? So if they both came from the denominator, both of those terms should be subtracted, okay? All right, so we have it all expanded out as far as we can with addition and subtraction. Now we just need to get rid of any exponents we have. So now we're going to look at our powers, right? Notice I have the 1/3 power here that I can bring down, and I have the square on the x that I can bring down. So now my problem is going to look like 1/3 log x minus 2 log x minus log z. Okay, not too bad. And normally this is where we would stop because we completely expanded it as far as we can go with addition and subtraction, and we've we've brought down our powers, right? But in this specific example, we can actually go a little bit further because we have like terms, right? These are, oops, my pens aren't working. These are like terms, okay? So in other words, I have 1/3 log x minus 2 log x, which gives me how much log x, right? Or in other words, I need to combine 1/3 minus 2. So in your calculator, you can do 1/3 minus 2 if it's able to do fractions. If not, you can get a common denominator by writing this as, 2/1, which would mean we need to multiply on top and bottom by 3, right? So this is 1/3 minus 6/3. Right? 1/3 minus 6/3 gives me negative 5/3. So when I combine my like terms here, I end up with negative 5/3 log x minus log z. Okay? And that's as far as I can go. Okay? So I know that was kind of a whopper of one to start with, right? Because it threw everything at us. We had to expand into addition. We had to expand into subtraction. We had to convert from a radical form to a fraction exponent. Then we had to bring our exponents down, and then we had to combine like terms. So that was everything that I could possibly throw at you, okay? So let's look at an easier one that hopefully we won't be terribly offended by. All right, here we go. So this one is log base 2, and we have a quotient 4 over the square root of x. So the first thing I notice is that it's a fraction or a quotient, right? And we know that division, or that a quotient, turns into a subtraction of log terms. So I'm going to go ahead and break this up into 2 separate log terms that are being subtracted. So I do log base 2 of the top factor, which is 4, minus log base 2 of the bottom factor, which is the square root of x. And I don't usually put parentheses around my radicals because the radical is its own little like grouping symbol. If you want to put parentheses around that, you can. Okay. All right. Now I want to see what I can simplify. I don't have any powers, it looks like, to bring down, but I can do a little simplifying because notice here I have a log base 2. And 4 happens to be a power of 2. So I can rewrite this as log base 2 of 2 squared, right? and then my log base 2 and 2 cancels, right? Or you can think about bringing that 2 down. Either way, this whole term is just going to turn into a 2. Okay. On my second term, this is log base 2 of the square root of x. Now here, I need to go ahead and convert this. Okay. I want to write this with a fraction exponent. Okay. And remember, the way we do fraction exponent is we do the power over the root. So if I look at this one, the power of x that I have, well, I only have one copy of an x. This isn't an x squared or an x cubed or an x to the 89th, right? This is just an x to the 1. And then my radical, if there's no number written inside this radical in that index point, it's considered a square root, right? If there's no number there. So I can rewrite this as log base 2 of x to the, if I write it as power over root, oh my gosh, this pen's killing me, to the 1/2 power. Okay, so I just rewrote this square root with a fraction exponent. And the reason I want to do that is so that I can now take this exponent and bring it down as a coefficient. Okay, so that's going to be my last step. So I have the 2 that is from all this mess, minus, when I bring down that 1/2, I get 1/2 log base 2 of x. Okay. Now notice that 1/2 is stuck like glue to this log. This is its own term. The 2 is its own term. This is its own term. So don't do 2 minus 1/2. You can't do that. Okay. 1/2 is stuck to the log. This is one piece, and the 2 is its own piece. And nothing is going to cancel out this log base 2 because I just have an x inside. So on this one, that's as far as I can go. Okay. So hopefully way less offensive than the first one, right? Okay. Let's look at a natural log. Natural log, again, the first thing I see is that this has a fraction, right? Or a quotient. So if it has a quotient, we know that turns into subtraction. So I'm going to rewrite this as 2 natural log terms being subtracted. So I do natural log of the top minus natural log of the bottom. Or in other words, ln of e times the cube root of x squared minus ln of 4. Okay. Now some of you right away may see, ooh, there's an e. An e and ln cancel. You are thinking right, but we cannot cancel the e and the ln here or here because there's still other stuff inside that log. Okay, we can only cancel the e if it's the only thing inside the log. Okay, so notice when we have an e and a radical and they're written side by side, right? What that is this is a multiplication, right? When you see two things side by side, that's a multiplication. And we know that multiplication turns into addition. So I can convert this to 2 natural log terms being added together. So this becomes the ln of e plus the ln of the cube root of x squared. Okay, everybody with me? So I just took this one. Since there's 2 things being multiplied using the product rule, I can write that as ln of the first factor plus ln of the second factor. And the last factor I'm just going to leave the same, ln of 4. Okay. All right, so let's see what we can do. Now that the e is by itself, now I can cancel these. But I can't just mark through it and poof, it's gone, it's 0, right? There was something there. So remember, when we cancel them, we're left with the exponent. So right now the exponent on the e is a 1, right? We have 1 e there. So if we cancel ln and e, we should still be left with a 1. Okay, plus, now this one I'm going to have to write with a fraction exponent, right? In other words, I want this as ln of x to some power. And to figure out what our power is, we look up here. Our shortcut is that if we want to write it with a fraction exponent, we use power over root. So looking at our radical here, the power on my x is a 2, and I'm going to write that over the root, which here is a cubed root. So I can rewrite this as x to the 2/3 power, okay, minus ln 4. And excuse me, ln 4 I can't simplify, right? Because ln is base e, 4 is not some power of e. So the only thing I have left here that I can do is, well, I guess I could simplify the 4 a little bit, right? Technically, because 4 is 2 squared. That doesn't help me cancel out the ln, but it is a way to simplify. So let's rewrite this as 2 squared, right? Because then I can bring down both powers. If we technically want to get it as simplified as possible, we need to bring down this 2/3, and we need to bring down this 2. Okay, so that's going to leave me with 1 as my first term. My second term becomes 2/3 ln x, and my last term, when I bring the 2 down, I get negative 2 ln 2. And that's as far as I can go here. Okay, so for whatever reason, expanding seems to be a little bit more difficult than condensing, but I believe you guys can do it. All right, so go ahead and pause the video, and there are 2 for you to try on the next page. Okay, whenever you're ready to check yourself, or if you get stuck, unpause it and we'll go over it. Okay, let's go ahead and see how you did. On the first one, again, kind of like all the other ones, we saw a fraction popped out at us, right? Or a quotient. So if I separate this into a quotient by making it into a subtraction of terms, I get log base 10 of the top, which is x, minus log base 10 of the bottom, which is the square root of 10. So log base 10 of x is not going to simplify. I don't have any power on x that I can bring down. X is not a power of 10, so I can't get rid of this log. So it's going to just stay there. However, on this term, what I'm noticing is that I have base 10, and here the square root of 10 is the same as 10 to a power, right? So I need to write it as its power over its root. So if I look for a power here, this is 10 to the first power, and my radical here is a square root. So I can rewrite this as 10 to the 1/2 power. Now, from this step, there's 2 ways to do it. Some of you might have just marked out log base 10 and 10, and you're left with the 1/2. Some of you may have brought down the 1/2 first and then marked that out. Either way, that log base 10 of 10 cancels, and you should be left with negative 1/2. Okay? All right, let's look at the second one. Second one was a little bit yuckier, but still doable. Trying to get that glare off. There we go. All right, so again, we started off with a quotient. Quotient turns into a subtraction. So we're going to write ln of the top of my fraction, right, minus ln of the bottom of my fraction. When we're expanding, we have to make sure we write the ln next to each piece, right? Okay, now here I can't do anything with this 3. This 3 is stuck to that, it makes it a cube root, right? So I can't bring a 3 down or do anything like that until I take care of this multiplication. This y and the cube root of x are being multiplied. Multiplication expands into addition. So I can write this as ln of y and ln of cube root of x, and those are going to be added, right, because this was a multiplication. On my second term, I have ln of e squared. Ln of e is, those are inverses, right? So that cancels, and I'm just left with the negative and then the 2 from the exponent. So that just becomes negative 2. Okay, and the last thing I need to do is bring down any exponents I have. The y didn't have any exponents, so I can just write it as ln y. And here, my radical, I need to write it with a fraction exponent. I had 1x under a cube root, so that becomes x to the 1/3 power. And then now that 1/3 exponent I can bring down as a coefficient. Okay, once I do that, you see I don't have any like terms, so that's as far as I can go on that one. Okay, all right, so I have one more thing to talk about in this section, and that is the change of base formula. And this is going to help us out a ton. Okay? Because when we are looking to solve logs, if we don't have a log base 10 or a log base E, there's nowhere to plug it into our calculator. That is an issue, right? Because we are only given a log button, which is base 10, or an ln button, which is base E. So if we need to solve something that looks like this, log base 7 of 15, I can't punch that into my calculator and get an answer without using this change of base formula. Now, what this says is that I can take any base B and change it to a new base using this formula. So let's say I want to change it to base A. What I do is I do whatever base I want to change it to is what I'm going to use on top and bottom. So I would do log base A of my original inside value over log base A of my original base. Now, I personally cannot think of one time that I would want to change a log from an odd base like 7, right, to another odd base like 14. Like, that would just be weird. I don't know what the point of that would be. So we're really not probably going to ever use this in this class. The reason we would want to change a base from something like 7 is so that we can punch it into our calculator. So the things I would like to change it to would be a log base 10 or a log base E, which is our log or our natural log. And notice the formula is the same. If I take log base B of X and I want to change it to a common log, right, this is our common log, then I just do common log of my original inside value and I divide it by the common log of my original base. Okay? Or you could do it with the natural log. Either way, natural log, either way you'll get the same answer. You can do natural log of the inside value over natural log of the base. Basically what you need to remember is that you do the inside value on top and you do the original base on bottom. Okay, so whether you use log or ln makes no difference to me. I'll work one using both. Okay, so let's look at this first one. It says evaluate the following log expressions. Round your answer to 3 decimal places. You do not want to round until the very end. Okay, for those of you who are having to work this piece by piece, don't round till the end. Leave all the decimals on your calculator. So if I want to do this, and I want to change this into something I can punch into my calculator, like the nice log button, right? The LOG, then I can convert this to natural log. And this formula says to do log of my original inside value, which here would be 15, divided by log of my original base, right? Which here is 7. Now, for those of you who have a scientific calculator that looks like this, or even this, okay, if you have one of these calculators or a Casio, you probably can do this all in one step with no problem. If you don't have a scientific calculator like that, if your calculator looks something more like this guy, right, then you're going to have to do it in steps, okay? If your calculator looks like this guy, you're going to have to get a decimal for this top value and a decimal for the bottom value and then divide those, okay? I suggest using the store button. So I'm going to show you one just that I have to work all the way out in case you have this type of calculator, and then the other one I'll do with the regular. So I'm going to go ahead and do log of 15, okay? So if I do log, oops, this maybe not. My calculator may have died. It died. Okay, so what I would do is I would do log of 15, or actually I'm going to do the bottom first. Okay, so I'm going to do log of 7 and see what that equals. It equals that mess. So I'm going to go ahead and write on the bottom here, this is 0.08509 and some more stuff, right? And then if you have a, I'm working this out like for if you have a calculator like this, okay? Mine died, but I can still show you how to do it. Now I would keep as many decimal places as you can here. I'm only gonna write out like 5 If you write out like 5, 6, 7, that should be enough to get you the right answer, but I would keep as many as you can on your calculator. If you have this calculator, once you get that answer, you can store it. See this STO? You can store it in one of these numbers, and then when you calculate the top, then you can recall the bottom and be able to keep all those decimals. If you're not sure on that, you can email me, text me, whatever, and I'll help you with that, okay? And then you would do the top. So here we would do log of 15, which is like 1.17609 and some more stuff. And then once you have, you know, a decimal approximation for both pieces, then you could divide them, okay, and get your answer. For the sake of time, I'm just going to write out what it is, which is 1.39166 and some more stuff. And then notice our instructions told us to round to 3 decimal places. So 1, 2, 3. This is my 3rd decimal place because there is a 6 behind it, and 6 is 5 or bigger. I'm going to go ahead and bump that up to a 2. So I'm going to say this is approximately 1.392. Okay, so now we're able to get a decimal approximation for a log that otherwise we wouldn't have been able to calculate. Okay, so let's do the same thing here. I'm going to go ahead and write it out. Now this one I did with common log, but remember, it doesn't matter if you use the log button or if you do the ln button, as long as you're doing that chosen log, okay, evaluated at your original inside value divided by your chosen log evaluated at your original base. So just to switch things up, I'm going to do the ln this time, okay? So I do ln of my original inside value. So this would be ln of 5 divided by ln of my original base, which here is pi. Now, anytime you see pi, you don't want to approximate and use 3.14. You want to use the pi button on your calculator, right? So if I look at my calculator here, I'm going to go ahead and type in ln 5, and then notice it opened parentheses for you. Make sure you close those parentheses, otherwise it's going to think whatever you type next is still inside the log, and we only want 5 inside the log, right? And we can go ahead and divide by whatever's on bottom, which here is ln of pi, and notice you should have a pi button on your calculator, which will have a ton of decimal places for pi versus 3.14, right? Okay, so when we hit equals, and we can see that we should get 1.4059 and some more stuff, and then we're going to approximate it to the 3rd decimal place, 1, 2, 3, which is at my 5. Notice there's a 9 behind it, so that's going to bump this up to a 6. So we're going to say this is approximately 1.406. Okay? Not too bad. All right, so there are 2 at the bottom. Go ahead and, again, on an exam, when I'm grading something like this, I am going to look that you at least wrote this. Okay? If you went straight from log base pi of 5 to an answer, I'm not going to give you credit for it, okay? Because if it says to use the change of base formula, I'm looking for this step, okay? So make sure you show me this step before you give me your answer, okay? And even better, show me this step. That way if you make a rounding error, I'm not going to take very much off of it, okay? All right, so go ahead and do those 2 practice problems. When you're ready, unpause the video and I will show you the worked out version, okay? All right, here we go. So here I use log. If you used ln, that's fine. I did log of my original inside factor, which was 3, over log of my original base, which was 1/2. Now, from here, you should be able to plug this into your calculator and get this answer. For those of you with a more basic calculator, you need to calculate top and bottom first. Okay, your answers here will differ from mine if you used ln instead of log, okay? But you should come out with the same answer at this step regardless. And then we round it to the 3rd decimal place, which gives us negative 1.585, okay? Number 2, you could work 2 separate ways. Here we actually don't even need a change of base formula, right? ln is a button on our calculator. We have an ln button. So here you could have just done ln of pi and got your answer and rounded it. Or if you didn't think to do that, We could change it to log. Log is another button on our calculator, right? And to do log, we would do log of our original inside value, which is pi, and then we would do log of our original base, which here the base of ln is e. And you can go ahead and calculate that, and you'll get the same thing either way. Okay, but if they do give you one to calculate and it's already a button you have on your calculator, just calculate it. You don't have to do change of base on those. Okay. All right, so that is the end of section 5.4. So you should be able to do that assignment now. Let me just double check that there's not a worksheet. I don't believe there is because there's no graphing, but it never hurts to check. Okay, so 5.4 is just a My Math Lab assignment. If y'all have any questions, please let me know.